Hello guys, welcome again to our lectures. So in this lecture we're gonna continue our non-leaf procedure, and we're gonna explain another example number 2, which is a little bit more complicated. This procedure or function is basically recursive function, okay? And one famous application for recursive function is basically factorial. So let's remind ourselves what factorial is. So if you have, for example, factorial of 4, that means 4 times 3 times 2 times 1. Like for example this will be 24. So in general, factorial of n is basically n multiplied by n minus 1, n minus 2 until 3, 2, 1. Okay, that's basically the factorial. So as we see here, factorial of n is actually equal to n times factorial n minus 1. And the factorial n minus 1 is actually n minus 1 times factorial n minus 2. Like for example here, factorial of 4 is basically factorial is 4 multiplied by factorial of 3, because factorial of 3 is 3 to 1. And the factorial of 3 is basically 3 multiplied by factorial of 2, because factorial of 2 is 2 times 1. And from this notion or idea came the idea of recursion. That if you have a function that can calculate factorial of n, it can calculate factorial of n minus 1, it can calculate factorial of n minus 2, and that's basically until you reach 1. Okay? And that's basically will be our stop criteria. So in the C code here that calculates, we have very simple codes that calculate factorial of 4. Okay, fact is actually a factorial function here that receives this 4, and then if n equals, there are two return. You can do return in two separate instances. The first instance when n equal to 1, in that case you're gonna return 1, because factorial of 1 equal 1, of course, 1 multiplied by 1. Okay, else you're gonna return n multiplied by factorial of n minus 1. n factorial of n minus 1. Okay, so that's basically how the recursion will work. In order to code this in assembly, it will be complicated to code it in that way. So first we're gonna convert this this simple C code into much obvious or clearer C code, and then try to basically code this new C code that we're gonna demonstrate in a moment. So the first step is to convert this into that. This is just an equivalent code, but easier to be translated into assembly. So let's check here. So I'm saying here return. So the first part, return if n equal to 1, return 1. That's no change. But return n factorial n minus 1, I have changed this a little bit, but it's equivalent. So what I have done here is basically I called n minus 1 q, and so this is q, and I called fact n minus 1 z. So z is equal to fact of q. Then I called n multiplied by fact n minus 1, or nz w. So w equal to nz. Then I return w. That's basically what we have done. So it's 4 steps in one line in C. Of course, this is C. So I just decompose this one line into 4 equivalent 4 lines, and that will be basically very easy to code. Actually, straightforward to code. You can just forget about the recursion and just try to translate this C code into assembly, and it will work with you. So before we go to assembly, let's verify, or imagine how, the recursion will work. So I'm gonna explain this in the C. So in the beginning, we're gonna pass the 4, fact of 4. So I'm gonna say if 4 equal to 1, of course it doesn't equal to 1, so I'm gonna go to else. So I'm gonna remove n and put 4. So int q equal to 4 minus 1, so q will be 3. So int z equal to fact of 3. So we need now to calculate factorial of 3. So we're gonna go back to the factorial function and do that. So that's basically the recursion. So I'm gonna stop here until calculating factorial of 3. So we're gonna go and remove n and put 3 now. If 3 is equal to 1, it's not equal to 1, so I'm gonna go to else. And q equal to n minus 1. N here is 3, remember. So q will be 2. Z equal to factorial of 2. And we're gonna stop here. Why? Because we don't know factorial of 2. We should go back and do this. That's basically what we're gonna do now. So we're gonna calculate factorial of 2. So I'm gonna remove n and put 2. If 2 equal to 1, it's not equal to 1, so I'm gonna go to else. Q equal to n minus 1. Remember now n is 2. 2 minus 1 is 1. So q here is 1. So int z equal to factorial of 1. I'm gonna stop again because I don't know factorial of 1. So we should again call factorial with n equal to 1. So here it is. Now n equal to 1. So if 1 equal to 1, of course 1 is equal to 1. So I'm gonna return 1 now. And we're gonna now go back to the original procedure until we reach, int fact int 4. The original, call. So I'm gonna go back now from return 1 to the caller. The caller of that one was int fact int 2 when n equal to 2. Because we stopped here because we didn't know what is factorial of 1 is. Now we know that factorial of 1 is actually 1. So z is equal to 1 in that case. So I'm gonna continue. So now int w equal to nz. Remember this is nz. N is 2 in that case and z become 1. So we're gonna return 2. Return to what? Return to the function that called fact int 2, which is fact n3. This is a recursion. So yes. So here is yes, here it is. So this is we stopped at int fact int 2. We calculated w, and in that case it's 2. Then we're gonna go to the caller. We're gonna go to the caller because when we calculated fact int 3, we stopped at z equal to fact of 2. Now we can continue because fact of 2 is actually 2. So we will calculate w, and then w is equal to 6. So I'm gonna leave it 3 by 2 to show you that at the end we're gonna have 4 multiplied by 3 multiplied by 2. Then we're gonna return this. Return to what? Return to int fact int 4. Here it is. So we stopped here. Now we go back to the caller. The caller was int z equal to fact of 3. Okay. So now fact of 3 is 3 multiplied by 2, which is basically 6. Now we can remove the z and put 3 multiplied by 2, and the n in that case is 4. Now we're gonna return 4 multiplied by 3 multiplied by 4, which is basically 24. Return to what? Return to the original caller, because this is int fact int 4. So if we continue, we go back, and that's it. We calculated x. That's an overview of how the recursion will work with you. Now let's go back and let's go forward and translate the functions that we have into assembly code. So for the main has no problem. So basically we're gonna put in A04 and then we're gonna jump and link to fact. So we're gonna now code fact. I will not go line by line, but I'm gonna show you how we translate the code. Then we're gonna go with an example and see line by line how the code will work and reproduce really 24, which is factorial of 4. So in the beginning we had this line here: if n equal to 1, return 1. That's basically what we're gonna do. So in these two lines, so I'm gonna put 1 into 0, then compare a0, which is n. Remember, this is n. This is n here. So we pass our argument n in a0. So I'm saying here, if a0 equal to which is 4 equal to 1, go to finish, but it doesn't equal to 1, it's a 4. So I'm gonna continue. So continue means we're gonna translate this code into assembly. We know for sure that this is a non-leaf function, so we're gonna overwrite the address RA. So in the beginning we must store RA into the stack. So that will store for us RA into the stack, the original RA, which is basically 08 in the first call. Then we continue. The first line here is int q equal to n minus 1. Then the second line is a recursive call for the factorial function. But we're gonna call it with n minus 1, not n. So basically we're gonna overwrite a0 here when we do the factorial again. That's only the first call. So again we should store a0 into the stack. Then because after the factorial here we're gonna return and use n, not q. So after the call here we should restore a0 from the stack and do the calculation. Okay, so to do this one here, this calculation, we store the first a0 into the stack. Good. Then after that we do the calculation qn equal to n minus 1 or a0 minus 1. So basically what I'm gonna do here, I'm gonna add a0 to minus 1 and assign the result to a0. So a0 now become a0 minus 1 or n minus 1. Then we code this one: int is equal to factorial of q. So we're gonna just call the factorial function. That's basically what we do here. After the call we should do this calculation. This calculation depends on n. Remember, n is in the stack now, so we should restore it first. That's basically what we did. We restore and increase SB. Then we do this calculation. This calculation is basically a multiplication. Okay, so remember the final return, which is w, it's gonna be v0, for example. We know that in procedures in MIPS we return our results in either v0 or v1, or v0 and v1 combined if the result is 64-bit. Okay, we are assuming here that the result will be 32 bits, so we're gonna return in v0. So we're gonna multiply. Mul is in a MIPS multiplication. v0 equal to n, which is a0, multiplied by z. What is z? Z is factorial of q, which is n minus 1. So it's like n in the first call, this will be n multiplied by n minus 1. What is n minus 1? It is the result of factorial of n minus 1. And the factorial function is the same. And all the time it returns a value into v0. So when I say mul v0 a0 v0, this is basically n minus 1 and this is basically n. Then in the next calculation it will be n minus 1 and n minus 2. In the third iteration it will be n minus 2, n minus 3, and so on until we multiply 3 by 2 and 2 by 1. Then we stop. After that we return to the to the main function, to 0, 8. So in that case we should restore RA from the stack and increment SB and make the return. One thing that we forgot to mention here is these two lines. So we said here, if n equal to 1, return 1. Okay, so we did the comparison, but we didn't see this finish label. So here is the finish label. So when we do the finish here, basically we're gonna add we're gonna set v0 to 1. Then we jump back, and the jump here will be basically to 208, as we're gonna see in the in the code. So let's now go step by step or line by line with an example. Okay, we're gonna assume that the stack pointer has 300 in the beginning, so that's basically stack pointer. So so whenever we finish, we should be back at the same location again. Okay, let's go line by line here. We're gonna calculate factorial of 4. So add A0, 0 and 4, so A0 become 4. Jump and link to fact, so we're gonna go here. This is jump and link, so we're gonna set RA to the following address which is 08. So RA will be 08. In fact, add I T001, so T0 will become 1. Branch equal A0 T0 finish. Does 4 equal to 1? No, so we will not go to finish. We're gonna continue. Add I SB minus 4, so this will be 296. Now the stack is pointing to that location. Store RA 0B, so we're gonna store RA into 296. So this is basically some mistake here, so this should be 296, 292, 288, 284, 280, 276, 272, 268, 264, 260, 256, 252, 248. Sorry for this, because of course the stack as we go down it decrement. Okay, no problem. So we're gonna store RA in the stack, so we're gonna store 08 here. Okay, and then we decrease the stack again, so 292. So we now going to do that location. We're gonna store A0, so we're gonna store 4 here. Add I A0 minus 1, so A0 become 3. Jump and link, so we're gonna store the 232 in RA to fact, so we're gonna go to fact again. So in fact, add 0 to 001, so again T0 become 1. Does 3 equal to 1? No, so we're gonna continue. Add I SB minus 4, 288. Store RA, so now we are pointing here. We're gonna store RA here, 232. Add I SB minus 4, 284. We now here store A0 in that location. So we're gonna store 3 here. Add I A0 0 minus 1, so A0 become 2. Jump and link, so again 2 3 2. One may say it's the same value, why you should write it again? So you know the processor is dumb, so it just overwrite what's in there, either they are equal or not. Then we go back. So when we go back here, add I. So again T0 is 1. Then we compare 2 doesn't equal to 1 to 80. Now we are here. Store RA 232 276. We are here. Store A0 2. Jump is, so this is become 1. Jump and link to fact again 232, because we make jump and link. We're gonna go back here. Now you're gonna see how the recursion work, and we're gonna see now because now E0 is equal to 1, so we're gonna see the recursion. It will be very interesting. So T0 is 1 again. Now we continue and compare T0 and A0. 1 equal to 1, so we're gonna go to finish. We're gonna go to finish. And remember, branch equal doesn't change array. So array will keep, 232. So we go to finish now. Add I V0 0 1. So V0 now appears to us and become 1. Then we jump register array. So we're gonna jump to 232. What is array? Array is 232. So we're gonna jump it. 236. This is not 232. Yes, 232. Yes. In 232, we're gonna now this is basically W equal to N multiplied by Q, or multiplied by Z. So basically that's we're gonna do now this step here. Int W N multiplied by Z. Let's check. So in 232, what we're gonna do, load word is 0 SB. So SB is here. So we're gonna let me do the recursion with another color, so it will be much clearer for us. So let me do it with this color here. So we stopped here, so SB is equal to 276. This one here. So we're gonna read this value into A. 2. Then we're gonna add 4. So now this is can be considered the free location, can be overwrite. So SB become now 280. Then we multiply V0 A0 so multiplied A0 and V0. V0 is 1 and A0 is 2, so basically V0 will become 2. Remember now, look, this is 2. I'm gonna write it above here. So in the beginning, the first multiplication is basically 2 multiplied by 1, which is really nice, because we're gonna see the series until we reach 4. 4 multiplied by 3 multiplied by 2 multiplied by 1. So V0 is 2. Then we're gonna load word RA and 0 SB. So we're gonna load this into RA. And then increment SB. So SB now is here. Then we jump register RA. What is RA? 232. So we're gonna go back again to here. Sorry. Because this is a recursion. All the time we stopped at Q equal to, or Q equal to fact of Z equal to fact of Q. And Q is N minus 1. So all the time we go back here. So load word A0 0 SB. So we're gonna load 3 into A. We're gonna add you know, SB and 4. So this is all, and we are pointing here now. Mul A0, which is now how much? Which is now 3. And what is V0? V0 is 2 multiplied by 1, which is 2, of course. So this will be 3 multiplied by 2 multiplied by 1, which is 6. Load word RASB, now RA change it to 232. And add SB4, so this is overwrite. Now we are pointing to 292. We jump register RA, so we're gonna go back to 232 again here. Load word A0, so we're gonna load now 4. Add SB4, so basically we're gonna point to here. Mul A0 is now 4 multiply. This is V0, which is 6, of course. And this is A0 is 4. So this is 4 multiplied by 3 multiplied by 2 multiplied by 1, which is basically, it's a factorial of 4. It's really neat. Then load word RASB. Now RA is 08. Because we finished, we should go back to the main function. This is 24. This is the factorial of 4. And we should also reset SB to its original location, which is 300. And then jump register RA, so we should jump to 08, which is that line here. That line here. Add S00 V0, so of course V0 24, we forgot this. So 0 will be 24. And that's it, guys. That's it. Of course, I didn't continue on that column here because there is no sufficient, but basically this will be like 284, then 288, 289, 296 until 300. So, but there is no much space. Okay, guys, that's it for this code. Just one note here before we finish. In the book, this is the code in the book. Of course, they are all equal. They are all the same. But the type of coding in the example you explained is much easier to understand and to follow, because it just a direct translation from. It was a direct translation from the from the C code, as we see. Okay, guys, thank you very much for watching, and see you in the next video. Bye bye.